Thank you for the opportunity to present our work today. My name is Lee Gable. I'm a postdoctoral fellow at the University of Calgary in Dr. Boyd's lab, where I'm studying the effect of spaceflight on bone microarchitecture and strength. Today I'll be presenting results from the T-bone study. This work is funded by the Canadian Space Agency and involves co-investigators from NASA and ESA. When astronauts embark on missions to the International Space Station, it's typically for 6 months at a time. Bone loss is a known consequence of spaceflight. We know prolonged exposure in microgravity leads to bone atrophy at a rate of 0.8% loss of BMD per month. So, over a 6-month mission, that loss is comparable to over a decade's worth of bone loss that would be experienced by older adults on Earth. Our study is specifically interested in better understanding the microarchitectural basis of how bone is lost during spaceflight. Our primary aim was to examine the effect of long-duration spaceflight on bone microarchitecture, density, and strength at the distal tibia and radius. We also aimed to determine the relationship between biochemical markers of bone turnover on changes in bone. T-bone is an ongoing Canadian Space Agency study out of NASA's Johnson Space Center. T-bone stands for three-dimensional bone and trabecular bone. In T-bone, we assess astronauts' bone microarchitecture and strength before spaceflight using high-resolution peripheral QCT. Crew members then embark on their 6-month missions to the International Space Station. Once they return, at R+0, we rescan their ankles and wrists, and then again we rescan at 6 months and at 12 months of recovery. At all time points, including during spaceflight, we ascertain urine and serum biochemical markers of bone turnover. Our pre- and post-spaceflight data collection is now complete. However, our recovery time points are still under investigation. So today I will present results of our pre- and post-spaceflight data in 17 astronauts. We imaged both the left and right distal tibia and radius using second-generation HRPQCT at pre- and post-flight. Second-generation XCT scans at an imaging resolution of 61 micrometers. We performed 3D image registration in order to examine common regions between baseline and follow-up. We examined measures of total, trabecular, and cortical BMD, trabecular microarchitecture, and bone strength estimated by finite element analysis. Urine and serum biochemical markers of bone turnover were collected through data sharing. Data were collected before spaceflight at 180 and 45 days prior to launch, on board at flight day 15, 30, 60, 120, and 180, and immediately upon return, R+0. Today I will present urinary markers of bone resorption, CTX and NTX, and serum markers of bone formation, P1NP, bone-specific ALP, osteocalcin, and a marker of osteocyte activity, sclerostin. I used Wilcoxon signed rank tests to examine changes in bone from pre to post-flight, and mixed effects models to examine trajectories of bone and biomarkers across time, as well as the relationship between biomarkers and changes in bone, controlling for mission duration. This study included 17 crew members. Average age was 47 years, ranging from 38 to 60. We had 3 females, 14 males, and median mission duration was 174 days, ranging from approximately 4 to 7 months, with about half crew members on missions less than 6 months duration. I'll now present results for how spaceflight affected bone outcomes. This figure depicts percent change in total BMD. Due to variability in length of time spent in space, percent change is normalized to a 6-month mission. Results at the radius are plotted on the left, the tibia on the right. The circles and triangles represent individual data points of crew members. Crew members on missions less than 6 months are in black triangles, and longer than 6 months are in red circles. Beside the data point is a box depicting median and interquartile range. What I hope becomes immediately clear from this image is that the weight-bearing tibia experienced much greater loss compared with the radius, a significant median loss of about 4% for total BMD at the tibia, and virtually no group change at the radius. It's also clear that most of the change at the tibia was driven by crew members on longer duration missions, so those red dots. At the radius, we see this dichotomy whereby those on shorter duration missions look like they're actually gaining total BMD, approximately 1%, whereas we're seeing comparable loss from those on longer duration missions. Because mission duration varied between 4 and 7 months, we were able to dig deeper into the effect of mission duration on bone loss in the subsequent figures. These plots depict actual loss in total BMD in milligrams per centimeter cubed on the y-axis by mission duration along the x-axis. Results at the radius are on top. The circles are individual data points, and the shaded area is the 95% confidence interval of the relationship between change in total BMD and mission duration based on the mixed model analysis. Specifically at the radius, we see a quadratic relationship with mission duration, depicting a slight gain in total BMD for missions approximately 4 to 6 months and loss on missions greater than 6.5 months. At the tibia on the bottom, we see a linear relationship between loss of total BMD and mission duration, indicating significant change for those on 5-month missions and longer. Bone strength and cortical BMD results were very similar to total BMD, where we saw a median 5% loss in failure load and 1 to 2% loss in cortical BMD at the tibia, as well as a linear relationship with mission duration. I'll now present results for trabecular BMD. Again, percent change is normalized to a 6-month mission. We saw no group change at the radius, but a significant 2% median decline at the tibia. Again, for the most part, that appears to be driven by those on longer duration flights, the red dots. We did not observe a relationship between mission duration and loss of trabecular BMD at the radius, but we saw a quadratic relationship between loss of trabecular BMD and mission duration at the tibia, such that there was no difference from pre-flight on missions less than 6 months duration, but accelerated loss thereafter. These are results for trabecular thickness, again percent change normalized to a 6-month mission, where there was no group change at the radius, but significant 1.5% median decline at the tibia. Again, we did not observe a relationship between mission duration and trabecular thinning at the radius or tibia. I'll now move on to results of the biomarker analysis. Biomarkers are on the y-axis against the measurement period on the x-axis, where you'll see pre-flight, flight day 15, 30, 60, 120, 180, and return r plus 0. Individual data points are in the open circles beside a box depicting median and interquartile range. Overlaid is a smoothing curve to show the trajectory of change over time. Bone resorption markers CTX and NTX are in the top left and middle and were elevated during and immediately after flight. Sclerostin is in the top right image, which was elevated mid-flight. Bone formation markers P1NP, bone-specific ALP, and osteocalcin are along the bottom panel and were elevated from mid-flight onwards. We observed a significant relationship between pre-flight CTX and P1NP with changes in total BMD and failure load at the tibia. In these plots, you'll see absolute change in total BMD on the y-axis and pre-flight concentrations of CTX and P1NP along the x-axis. Individual crew member data are in circles, and the shaded 95% confidence interval of the relationship between biomarkers and change in bone is in gray. The relationship was negative for CTX and P1NP, suggesting that greater bone turnover before flight predicts bone loss. Results were very similar for failure load. This study highlights the integral relationship between mission duration and bone deterioration. Our study confirms reports from DEXA and QCT regarding greater bone loss on longer missions. As most missions today are limited to about 6 months duration, it's unclear if bone loss would stabilize on longer missions or if it would continue to deteriorate. This is an area for future study. Reductions in tibia BMD and bone strength are similar to a previous study in Russian cosmonauts using first-generation XCT. However, that study did not observe the trabecular thinning that we did, which may speak to the increased resolution of second-generation XCT and its improved ability to detect changes in trabecular microarchitecture. Thinning trabeculae may underpin the losses we're observing in BMD and strength. Finally, elevated pre-flight markers of bone turnover may help to identify individuals most susceptible to bone loss on long-duration spaceflight. We suspect that bone already in a heightened state of breakdown and repair prior to spaceflight may be more sensitive to increased bone resorption and reduced formation in space. Perhaps these biomarkers may be useful as a pre-flight screening tool in future. With that, I would like to thank the crew members for their participation, the Bone Imaging Lab, and particularly our imaging techs, Anne, Stephanie, and Duncan. Thank you for your attention. I'd be happy to answer any questions.